and get started. And if other people join us midstream, they'll just have to swim faster. Let me put up our Buzz lessons here so we can look and see what's going on this week in our Algebra 3 class. If we look at the grade screen, going to scroll way down because we're almost at the end. All right, April 30th. That's this Sunday. We've got real zeros of polynomial functions and complex zeros. So we're talking about zeros this week. 8.03, 8.04 is what we have. Next week, we'll have the fundamental theorem of algebra and rational functions. And then got the semester final for those of you who are not exempt, which those exemptions are going to be, I guess, finalized real soon since we got 2 weeks of school left. So make sure your grade is above 75%. That is one of the requirements to be exempt. And then, of course, no more than 4 absences in here or in advisory. It may be too late for some of you on that one, but and no missing assignments. So if you didn't get some of these matrix assignments turns in and you're trying to be exempt, better go back and get those caught up. There was a bunch of matrix assignments there. Let's look at 8.03 and 8.04 this morning. Let's see what it's talking about. Close that matrix folder. We don't need that one. All right, real zeros of polynomial functions. Got a lot to cover today. All right, so we're going to look at the scenic overlook part. Remember, these assignments have, these lessons have a summary up here. The scenic overview kind of goes through the whole lesson in just like a summary view. And then when you get down to the page that has color on it, not blue, like right here, this page, which got all these little color dot squares, that's the beginning of the lesson, but it goes into more detail, gives more examples. So we're gonna review in class the scenic overview up here at the top, and then you can go through the lesson if you need more information, if you need more detail on that. So let's get up here to the top. You see there's a lot for the scenic overlook this week. So, all right, let's talk about the relationship between an x-intercept and a factor. So it gives us this function right here, f of x equals 2x to the third plus x squared minus 14x minus 21. And a graph shows that at x equals 3, that's a 0. So it crosses the x-axis at x equals 3. So we know that's a 0 for this function. That would mean x minus 3 is a factor. If x equal 3 is a 0, x minus 3 is a factor. So we can factor that out, which they've done over here with long division. See, now we need to review long division here, or polynomial. So let's do this one, and we'll do long division because we're going to divide it by x plus 1. So I'm going to write that on my paper over here so I can put it up on the screen. And we will go through the steps of long division again, because we have a lesson to deal with that has that in it and could be in your assignment. We're going to divide by x plus 1. All right, let me put that up here on our screen. Okay, so the first thing that's important is we have to make sure that we didn't miss any terms. X to the third, x squared, x, and 6. So there's no missing terms. If we didn't have an x, that would mean there'd be plus 0x, right? If there wasn't an x, if we just had 2x to the third minus 3x squared plus 6, we'd have to add the 0x because there is a 0x in there. But this time we have it all. So let me bring my line down just a little bit so we got room on the top of the page. Let's put it pretty high there, but squeeze that down a little bit. All right. So when we're dividing, I mean, if you remember how you divided, let's say 7 into 435. Let's do that. 7 into 435. Remember dividing. It won't go into 4, so we go over here. How many times will 7 go into 43? We'll go in there 6 times. So we write that above the 43 part. 6 times 7 is 42. And if you remember, we subtract this. 43 minus 42 is 1. Then we have to bring down the next term. How many times does 7 go into 15? It goes 2. 2 times 7 is 14. We subtract again. We have a remainder of 1. So 435 is basically 62 and a remainder of 1. Or it's 62 and 1/7. When you divide 7 into 435, it's 62 and 1/7 because you have a remainder of 1. Well, the same process works with polynomials. We look at the x and we see how many times it goes into here. Now, since we have an x plus 1, we're going to write our answer underneath the second term, just like we had to go over here because 7 didn't go into 4, so we had to go to the second term. How many times will x go into 2x to the third? Well, if we divide x out of that, we find it'll go 2x squared times. 2x squared times is how many times x is when you divide x out of that. So we'll multiply it now, just like we multiply 6 times 7 and put it underneath. We're going to multiply that times this. So 2x squared times x is 2x to the third. 2x squared times 1 is 2x squared. Now we're going to subtract that. We're going to subtract that. This is 0. So negative 3x squared minus 2x squared is minus 5x squared. And now we have to bring the next term down. All right, how many times does x go into negative 5x squared? It goes negative 5 times. Negative 5x times, because x squared. So negative 5x times x is negative 5x squared. Negative 5x times 1 is negative 5x. Again, we're subtracting this. So negative 5x minus negative 5x is 0. Negative 2x minus negative 5. If we subtract the negative, means you're adding. So this is going to be 3x. Bring this down. Plus 6. How many times does x go into 3x? 3 times. So 3x plus 3. We have a remainder of 3 when we subtract that. 6 minus 3 is 3. So when you divide x plus 1 into 2x squared, into 2x to the third minus 3x squared minus 2x plus 6, we get 2x squared minus 5x plus 3 plus a remainder of 3. So plus 3x plus 1s. Just like we had 1/7 over here, we have 3x plus 1s because that's what we divided by. So that's how long division works. If we look back at our problem, see, they got x plus 1 equals 2x squared minus 5x plus 3 plus a remainder of 3. And then they went ahead and they take this, since this is a quadratic, they factor it again. And it factors to x minus 1, 2x minus 3 plus 3. So if we're taking factoring to its fullest form, the first thing we can do is pull out one factor to get it to a quadratic, and then factor the quadratic, which they did right here. So that's an example of a division algorithm. It says, that means just we're dividing. It says the division algorithm states that if f of x, which is the function, and d of x is polynomials, which d is the divisor. This is a very mathy term, so hang with me. If f of x and d of x are polynomials such that d of x is not equal to 0, right? You're not dividing by 0. And the degree of d of x is less than or equal to the degree of the function, f of x, there exist unique polynomials q of x and r of x such that the function equals the divisor times the quotient plus the remainder. Where the remainder equals 0 or the degree of rx is less than the degree of that, if the remainder equals 0, then d of x divides evenly into f of x. For example, in arithmetic, if 14 divided by 3 is 4 with a remainder of 2, we can say that 14 equals 3 times 4 plus 2. So all this mathy division algorithm basically just says there's a divisor and a function, the quotient and a remainder. So the function equals the divisor times the quotient. Oh, I got to put times the quotient plus the remainder. So if we look at that, 435 equals the divisor, we divided by 7, times the quotient, well, that's 62, plus the remainder. So if we take 7 times 62 and add 1, we'll get 435. That's all it's saying. So over here, it's the same thing. The function equals the divisor times the quotient plus the remainder. Fancy math terms, just talk about basic math principles. We wouldn't generally think about it in terms. Divisor times quotient plus the remainder, but that's how it works out. So don't let it throw you off with those fancy math terms. That's all this division algorithms just talk about. How division works. We've been doing that since elementary school. We just haven't put it in fancy math terms like that. So synthetic division. Love synthetic division. It's a convenient way to do division of a polynomial by a divisor like x minus k. So you don't do that when you have like 2x or 3x or something like that. But if you just have x minus k, we can use synthetic division. So we're going to review that. You may have remembered it from Algebra 2, but if not, we're going to look at an example of that. Now, this technique works only for the divisor x minus k, not 2x or 3x, like I said. If you have a coefficient on the x, you don't use synthetic division. But remember, if you have x plus k, that's still the same thing. It's just x minus a negative. K is a negative in that case. So as long as you just have x, you can do that. So let's use synthetic division to try one of their ones that you can check the answers on here. All right, let's see. We'll do the first one or the second one. Let's do the second one because it's missing some terms. See, this has x to the fourth, x third, x squared, x, and the constant. This one is missing some. So let's write this down. And we're going to divide that by x plus 2. All right, so x plus 2. And we're dividing that into x to the fourth minus 2x squared plus 6. All right, let me put that up on the screen. So if we're going to divide this into that using synthetic division, first we have to know this is x minus k, and we're dividing by k. Well, if it's minus k and we got x plus 2, k equals negative 2. So that's what we're dividing by. Negative 2 is what we're dividing by with synthetic division. And we're divided into this. So all we're going to do for synthetic division is take the coefficients. This has a coefficient of 1. This has a coefficient of negative 2. And the constant is a 6. But here's the problem. We don't have an x to the third. And we don't have an x. So we have to remember what's their coefficient. So the coefficient of x to the fourth is 1. The coefficient of x to the third, since it's not appearing in the function, is 0. Then the x squared term, well, the x squared has a coefficient of negative 2. Then the coefficient of the x term, well, it doesn't show up in the function, so it has a coefficient of 0. And then we have the 6. So all we need is the coefficients. Start with the largest term and make sure you have every other term represented. X to the fourth, x to the third, x squared, x, and the constant. All right, so a reminder on how synthetic division works. The first term just comes straight down. Always. Whatever the coefficient is, that first term. And then we multiply. Negative 2 times 1. Okay. Then we add. We always add this way. We multiply this way. That's negative 2. Now again, we multiply. Negative 2 times negative 2 is 4. And we add. Negative 2 plus 4 is a positive 2. Multiply again. Negative 2 times 2 is negative 4. Add 0 plus negative 4. And then finally multiply again. Negative 2 times negative 4 is a positive 8. And add 14. Well, that's our answer, but we haven't written our answer as a function yet. So if we want to know, if we divide x plus 2 into this, what does that give us? Well, so the factors are x plus 2 because we just factored that out. And what's left? Since our original was an x to the fourth, that means this is the coefficient of x to the third because we divided one of the x's out. So we subtract 1 from this. So the coefficient's 1. So it's x to the third, 1x to the third, minus 2x squared plus 2x minus 4. And we have a remainder plus 14x plus 2s. When we divide this into this, we get this with this remainder. Kind of like we had a remainder up here of 1. We had a remainder here of 3. We have a remainder. If this last number would have been 0, then that would be our answer. And this would actually be a factor. That would actually be a 0 of this original function, because it would divide evenly. That means it's a 0. Since it has remainder, this is not a 0. It is not going to cross the x-axis at -2, because this is not a solution for that function. But that is how, I'll erase that 0 there. That is how synthetic division works. If you need a reminder of that, I can post a video in Google Classroom to just give you a refresher on that too. But that is synthetic division. So let's go back and see what they're doing with that now. So check your answers. You can click on that if you do A and B, and it'll give you the answers here so you can double check yourself. X to the third plus 4 squared plus 4x plus 9 with a remainder of 12. Was that the one we did? Oh, how come they got a different? Oh, I did the second one. I did the second with a remainder of 14. 1, -2, 2, -4, 14. Yeah, that's right. That's what we got right there. X to the third, the remainder of 14. So you can check yourself if you want to do that first one to see if you're doing it right. All right, let's talk about the remainder theorem. We've got lots of theorems this week. If a polynomial is divided by x minus k, and the remainder is f of k, r equals f of k, that means we can find a point on the graph. Now, here's what's really cool. Here's what's really cool. I'm going to show you using this right here. We said that since this has a remainder, this is not where it crosses x. But it does mean that the point -2 and the remainder 14, this point does exist. Because when we divided by -2, we had a remainder of 14. So the remainder theorem says that goes as a point on the graph. -2, 14 will exist on this graph. So let's look at that then. Let's graph that. I want to see this work out here. So let's graph that. I graph x to the fourth, the original equation, minus 2x squared plus 6. It says -2, 14 is a point on the graph, because that was our remainder when we divided by -2. There it is. That is a point on that graph, -2, 14. The remainder theorem is that's pretty cool. You probably haven't seen that before in math, but that's a useful thing for synthetic division to find out what the y coordinate is. We can divide that in there. And it says it's not a 0. In fact, this equation has no real zeros. All of its zeros are imaginary zeros, because it does not cross the x-axis anywhere. So that's interesting too. So the remainder theorem shows that we can find a point on the graph by dividing by that using division, and the remainder will be the y coordinate. So our -2 gave us the coordinate of -2, 14. All right. Then it gives you a chance to do that. Determine the value of the remainder, and then graph that. That's the equation we just did. Here's some other ones you can divide by in synthetic division and see if you can determine what the point is. Then you can look at the graph and check to see if you're correct. All right. So the factor theorem. Now we talked about the remainder theorem. Now the factor theorem. It says the factor theorem is f of x has a factor of minus k if and only if, that's a math term, if and only if f of k equals 0. So as we talked about on this, what I was mentioning a minute ago, -2 is only a factor if the remainder is 0. If the remainder is 0, that means that is one of the factors, and that would be a solution, or a 0. X plus 2 would be. But since we had a remainder, our f of k was not 0, So it is not one of the factors. We couldn't factor that out of that equation because it leaves a remainder. So, all right. So this says use synthetic division and determine if these are factors. Is x plus 1 a factor of either one of these? Is x minus 1 a factor? And again, you can check your answers. We're not going to take time to do that in class, but we got a lot to cover. But using synthetic division, just check to see if that's a factor, which all it means is the remainder 0 or not. All right. We're going to get into the rational zero test and Descartes' rule of signs. Descartes' rule of signs. So the rational zero test lets us take a shortcut to figure out if we're trying to figure out from a function what are the possible rational zeros. And again, there's a lot of mathy words here. I'm gonna show you what it's talking about without going through all the mathy part here. So it says if we have a function, and let's just create a function over here. Let's say we've got a function that is, yeah, we'll use 3. That's fine. 3x to the 4th minus 2x squared plus x minus 6. Okay, if we have this equation right here, this function, and we want to know, we're trying to figure out, okay, I need to find the factors of this. And I'm going to use synthetic division to do it, which means I'm going to divide a number into that. And if my remainder is 0, I know that's going to be one of the factors. So if I could divide -1 into there, I know if I get a remainder 0, x plus 1, because it'd be x minus k, x plus 1 would be a factor if -1 works. But I could sit here all day guessing numbers. Is 0 a factor? Is 1 a factor? Is -1 a factor? Is 2 a factor? Is -2 a factor? Is 3 a factor? Is -3 a factor? 4 a factor? Is negative. That's a lot of synthetic division. Well, the rational zero theorem helps us shorten that. So if we take the 3, what are the factors of 3? Well, just 1 and 3, right? And it's positive and negative. Could be +1 times +3. Could be -1 times -3, but 1 and 3. So we're going to call this the Q. Q is the factor of the first term, the largest exponent. And P, you ever heard of mind your P's and Q's? This is our P's and Q's right here. Is the factors of -6, which could be plus or minus again. 1 and 6 and 2. I'm going to put them in order. 1, 2, 3, and 6 are the factors of 6, because we can take 1 times 6, we can take 2 times 3, right? And plus or minus to end up with a negative. So it'd be a +1, -6, or -1, +6. Yeah, we can do all those combinations. But the only possible rational, not even rational, the only possible zeros, the rational zero function, is what are the P's over the Q's. So let's take this P and put it over all the Q's. So it could be 1 over 1, and they're all plus or minus. Could be 1 over 1 or 1 over 3. Again, they're all plus or minus. That could be a possibles. Now let's take the second one. Or it could be 2 over 1 plus or minus. I'll add all the plus or minuses in a minute. Or 2 over 3. Or 3 over 1. Or 3 over 3. Or 6 over 1. Or 6 over 3. All right, now let's simplify all of that. So the possible rational zeros. There could be some irrational zeros, but the possible rational zeros, plus or minus, well, what's 1 over 1? Well, that's just 1, right? That simplifies just to 1. Could be plus or minus 1/3. Okay. Could be plus or minus 2 over 1, which is just 2. Or 2/3, plus or minus 2/3. All right, I'm going to add on the bottom row here. Or 3 over 1, so plus or minus 3. Or 3 over 3. What's 3 over 3? That's 1. We've already listed that one. That's already been listed. Or 6 over 1, plus or minus 6. 6 over 3 is just 2. We've already listed 2. So that's a duplicate also. So here's all the possible rational zeros: plus or minus 1, plus or minus 1/3, plus or minus 2, plus or minus 2/3, plus or minus 3, plus or minus 6. So really, there's only 12 possible numbers that we could divide into there to find out if it is a factor, if it's a rational zero. We've narrowed it down. Instead of every number in the world, we know now that 0 is not even an option. So x by itself wouldn't factor out of there. We know 4 and 5 are not options, and all the other fractions in between there are not options. This is the only possible rational zeros. That's what the rational zero test is saying. So we can check. Well, let's get to Descartes' rule of signs first. Descartes' rule of signs. So what Descartes says is this is a method to determine how many real zeros a function has. And here's how it works. The number of positive real zeros will be equal to the number of sign changes between consecutive coefficients in f of x, or less this number by multiples of 2. All right, we're like, okay, Mr. Brock, what in the world are you talking about with that? Well, let me show you. Let me go back and write this original function again. 3x to the 4th minus 2x squared plus x minus 6. How many times does the sign change? We start out, this is a positive number, right? So, right there, it changed to a negative. That's one sign change. Then it changed back to a positive. Now we've got 2 sign changes. Then it changed back to a negative. So 3 sign changes, which means at most, we know this has 4 possible zeros. At most, 3 of them are positive real zeros. Which means if 1, 1/3, and 2 are all real zeros, we don't have to check 2/3, 3, and 6 because there's only 3 positive real zeros. Now, this hasn't told us how many negative zeros there could be, but that rules out all the rest of the positive numbers. Can't be positive 2/3, 3, and 6 if these first 3 worked. Once we find 3 positive ones, that's the most it could possibly be. But the theorem said, or, let's look at the theorem again, or will be less than this number by multiples of 2, which means multiples of 2. It means it could be 1 positive real zero, right? There's either 3 or 1. There's no other choice. There can't be 4. There can't be 2. There can't be 0. There's guaranteed to be 1 positive real zero or 3. And you're like, why are we doing that by 2s? Well, here's the thing. If it's not a real zero, maybe there's an imaginary zero. All right, so maybe it has a 0 at 2 plus 3i. Maybe when we do the math, we find out that this is one of the zeros. If that's one of the zeros, and this is a positive, it's a plus 2, that's a positive root, it's a positive answer. If this is a 0, then guaranteed its conjugate, if you haven't heard the term conjugate, its conjugate is 2 minus 3i. These always exist in pairs. When we're talking about a 0 of an equation, they exist in pairs. If you have the plus 3i version, the negative 3i version is also a solution. We would never have 1 imaginary 0. We would always have 2 or 4 or 6 or 8. Yeah, like on this, we can't have more than 4. But they always come in pairs. So if there's an imaginary solution and there's 2 of them, then instead of 3 positive real zeros, we only have 1. So we know there would not be more than 2 because there's at least 1 positive real zero. We just don't know yet if there's imaginary solutions, or are they all 3 positive real zeros? All right. Now, Descartes also says we can figure out how many negative real zeros there are by taking this equation. This is f of x. That's f of x. If we look at f of negative x, Well, that just means we go in for every x and we substitute the negative variety of that. So 3 negative x to the fourth power minus 2 negative x squared plus negative x minus 6. All right, let's simplify that. Negative x to the fourth power, it's negative x times negative x times negative x times negative x. That's a positive x to the fourth. So that's going to equal 3x to the fourth. Nothing changed because it's to the fourth power. It's an even power, so it's going to end up even. Minus 2 times negative x squared. Well, negative x times negative x equals a positive x squared because it's a negative times a negative. So this is negative 2x squared. Nothing changed. Plus negative x. Oh, that's a minus x. And we have the minus 6. So now how many sign changes do we have? This is a positive. That's a negative. There's a sign change. Negative to a negative, negative to a negative. It never changed again. So there is one negative real root, according to Descartes. There's 3 or 1 positive, and there's 1 negative. This is guaranteed since we couldn't have a negative imaginary root because we'd have to have 2 of them. We can't have one by itself. So we know there's a negative real root to this equation, and we know there's a positive real root, and there possibly is 3 positive ones. So let's check it without doing all the math and not checking all these and start dividing by that. Let's just graph this and see actually, I'm going to graph that equation right there and see how many real roots there are. All right, so we're going to go back to our Desmos. We're going to cancel that. I'm going to put 3x to the fourth minus 2x squared plus x minus 6. Well, there is our, oops, I'm going to do that. There, I'm going to close it like that. There's our equation. There are 1 negative root. See, because on the negative, let's see what it is. It's a decimal, but it's a real root. There's 1 negative one, and there's 1 positive, and it's a decimal. They're not, it's not going to be a lovely number. It's not a rational number. These are irrational roots. So the possible rational zeros, but it is a positive real root. And there's only one of each, which Descartes told us there should be 3 or 1 positive and there should be 1 negative. And that's right. So there's 2 imaginary. Since this is x to the fourth, there are 4 solutions. It's just 2 of them are imaginary numbers. And when we looked at the possible real roots, none of these showed up. So of those possible real roots, there are no rational zeros. They're both irrational, but they're real roots. They're just irrational. So let's go back to our assignment here. But that's how Descartes, and here's some examples too. You can click on there and get more examples of how Descartes' rule works if you want to go back through that again. And it'll go through this equation for you and talk about how many sign changes it has. So it'll show you looking at each one, how many sign changes. And then putting in the negative and how many sign changes. So there's some examples there if you want to get into that deeper. But rational zeros tell you how many possible rational roots there are, but it doesn't guarantee any of those will be zeros, which in our case it was not. They're all irrational, but this tells you how many it will have. So there's some that you can check your answers, find the rational zeros, doing the possible rational zeros test, and then use Descartes to rule it down. Now let's look at bounds, possible bound. Bounds is like boundaries, right? So here's another test for zeros. Is to look at the sign pattern of the last row during synthetic, when we do synthetic division. So we're going to do synthetic division on one. And we're going to look at the possible bounds. So let's see what they're looking at here. All right, so they have an equation. And we'll talk about the mathy part here after we look at this example. So they've got x to the third minus 7x minus 6. And they're going to, they look to see what the possible zeros are using the P over Q. See, it had negative 6 is 1, 2, 3, and 6. The first is just a 1. The coefficient of the x third is just a 1. So that's the only denominator. So the rational possible real zeros are 1, 2, 3, and 6. So they've got it narrowed down to 8 possible zeros. So they did synthetic division. They said, okay, let's try 3. So the first one they tried was the positive 3. And here's what they got when they used synthetic division. They did the 1, 0, -7, -6. That's the coefficients. Remember, there's no x squared, so they do 0. And when they did that, bring the 1 down, multiply by 3, add those, multiply by 3, add those, multiply by 3. All of these numbers on the bottom row are positive numbers or 0. Positive numbers or 0. So when that happens, that means 3 is an upper bound. There's no need to test 6 because there's no possible way that 6 is a real 0 for this. Because the fact that this ended up all 0, now let me write this down just so I can emphasize some things on that. 1, 0, -7, -6. Just to make sure you're getting this. So when they did synthetic division, make that bigger. When they did synthetic division, everything down here was a positive number or a 0. Positive or 0. So 3 is the largest rational 0. This 3 that we divided by is the largest because all of these are positive or 0. So we know we don't have to check the 6. The 6 was a possible solution for this equation, but 6 will have a remainder, guaranteed, because all these are 0 or positive. Now, in another situation, if we did -3, let's look at this using the same equation. I'm writing that down. If we do this synthetic division, bring the 1 down, multiply -3 times 1 is -3. Add those. That's -3. Multiply. Add those. Multiply. And that ends up -12. Now what happens? Oh, well, now we've got a +1 and -3, a +2 and a -12. Alternates. Plus, minus. Every time it alternates. Plus, minus, plus, minus, plus. Without fail. It doesn't go plus, plus, minus, plus. It's plus, minus, plus, minus. Alternate. So -3 is lower bound. The lower bound or smallest rational 0. There's no need to check -6. -6 is now ruled off the list. There's nothing smaller than -3 guaranteed that could possibly be a rational 0. Now, in this case, -3 did not work. It's got a remainder. It's got a remainder, but there's nothing less than -3 on there. See, when we look at that, -3 is a lower bound based on rule number 2, positive, negative, positive, negative. But it's not a solution. 3 is a solution. When we graph that, and we can graph that real quick, x to the third minus 7x. What else does that have there? Minus 6. There's that 3. It is a solution. We knew it was a solution. It said it was a solution because it had no remainder. And -2 and -1 are both solutions. Notice -3, it said, was a lower bound. It said it was not a solution. It didn't have a remainder of 0, so it was not a solution. But there's not going to be one smaller than that because it was positive, negative, positive, negative. So it turns out there are 3 solutions, and they are larger than -3. And they do not go larger than +3. So again, little shortcuts to help you rule it down. They didn't have to check 8 numbers there because 3 and negative 3, said, nope, nope, nope. It's got to be between 3 and negative 3. So that means just had to check these numbers. Right? And we could have used Descartes to rule it down even more. We could have went with Descartes and said, oh, there's only one sign change, so there's only one positive number. Starts as a positive, changes to a negative, stays a negative. So there's only one positive 0. So once we found 3, we don't have to check 1 and 2 and 6. Because Descartes said there's only going to be one positive one. And then we can put that negative x in there and see how many negatives, but we know there's only 3 total. So that kind of told us that. So that is all of 8.03. Let's look at the assignment that goes with that. I think it's just got 5 questions. This wants you to use synthetic division. What's the answer when you divide this by x plus 2? They want you to divide this by x squared plus 1. You cannot do synthetic division there because that's an x squared. It has to be just an x. So this you got to do long division and then rewrite it. So x squared plus 1 is one of the factors. Which one of these is it? And does it have a remainder or not? This one tells you to find the remainder. You can use synthetic division on this because it just gives you the k. You divide it by 3 with synthetic division. What's the remainder? And this says use synthetic division to determine whether this is an upper or lower bound. All right, so if you divide it by 4, is that an upper bound or a lower bound? Oh, this says, is it a lower bound? It wants to know, is 4 the lower bound? Is that the smallest possible rational zero? So you're looking for that alternating sign. And then this wants you to write a list of all the possible rational zeros. That's the P over Q thing. P over Q, what are the possible zeros for that? All right, let's look at our second lesson. It's shorter. I know we've been here a while already. Scenic overlook. Definition of a complex number. This is to talk about imaginary numbers. That's what a complex number. A plus BI. So let's look real quick at A plus BI. It says for the real numbers A and B, the number A plus BI is a complex number. If A is not equal to 0, or if A equals 0 and B is not, BI is an imaginary number. So we don't have to have the A part, right? Like 3I is an imaginary number, or 1 plus 3I are both imaginary numbers. As long as there's an I component, there's an imaginary number, complex number. And we can do operations with those. So let me talk about the operations we can do with those. So let's say we have a complex number of 2 plus 3I, and we have 4 minus 5I. So we have these two imaginary numbers. We know they're imaginary because they have an I component. If it was just 2, that'd be a real number. If it's just 3I, that's imaginary. 2 plus 3I, imaginary. Anything like that. What can we do with these two? We can add them together. That is possible. But there are rules to follow. You can only add the real parts together and the imaginary parts together. You cannot combine the 2 and the 3. This is not 5I. We can't put those together. This is a real number. This is an imaginary number. But if we add them, we can add the real part, 2 plus 4, and 3I plus negative 5I. But notice, we can only put the real numbers together, and we can only put the imaginary parts together. But we can very nicely add those together. By the same token, we can take 2 plus 3I and subtract 4 minus 5I. 2 minus 4, we have to do the real part. So that's negative 2. 3I minus a negative 5I. Minus a negative. So that means we're adding 8I. But we can do that. We can also multiply 2 plus 3I times 4 minus 5I. Multiply. How do we do that? Just like we always do multiplication of two binomials. We got to distribute, right? So 2 times 4, 8. 2 times negative 5I. negative 10i. 3i times 4, 12i. Now here's where it gets tricky. 3i times negative 5i. Well, 3 times 5 is negative 15. I times I is I squared. Oh, we've got to talk about I squared. Anyone remember what I is equal to? I, as an imaginary number, is equal to the square root of negative 1. In mathematics, that's what I is equal to. We cannot take the square root of a negative number. So that's why this is imaginary. So I is the same thing as the square root of negative 1, which means what is I squared equal to? Well, if we square that, that cancels out the square root, right? Because the square root of 9 can be canceled. If we square that, what's the square root of 9? It's 3. What's 3 squared? Well, it's 9. So if we square that, it just cancels out the square root. So this is equal to negative 1. Square root of negative 1 times the square root of negative 1 is negative 1. Square root of 9 times the square root of 9 is 9. So this can be rewritten as 8 minus 10i plus 12i minus 15 times negative 1. This became a real number. Because when we have I squared, it's a real number. It's not imaginary any longer. So this is now 8. These are like terms, negative 10i plus 12i plus 2i minus 15 times negative 1. So our final answer is 23 plus 2i. Because now this is a real number. And real numbers combine. So 23 plus 2i. Now, one last thing I'll talk about is dividing. Dividing is a little trickier. Because we need to get rid of the denominator. And the way you do that, the conjugate. Here's a good math term right here, the conjugate. The complex conjugate. We have to multiply by 1, but this is what our 1's going to look like. 4 minus 5i. Remember I said where these always come in pairs? These are conjugates of each other. What makes them a conjugate? Well, I'll show you. The fact that this one has the plus 3i and this has the minus 3i. That makes them a conjugate of one another. The conjugate of 4 minus 5i is 4 plus 5i. That's the conjugate. So we got to multiply by 4 plus 5i over 4 plus 5i. So this is just 1. That's 1. We're multiplying it by 1, but we're doing it very intentionally to change this denominator where it's not imaginary. So what does that equal? 4 minus 5i times 4 plus 5i. 4 times 4 is 16. 4 times 5i is 20i. Negative 5i times 4 is negative 20i. Notice those just canceled each other out. We've got a positive 20i and negative 20i. Negative 5i times positive 5i is minus 25i squared, or negative 25 times negative 1, which is plus 25. So the bottom becomes 41. We've just changed the denominator to a real number. So now whatever comes out on top comes out on top here. 2 plus 3i, and it'll be imaginary. 4 plus 5i. So 2 times 4 is 8. 2 times 5i is 10i. 3i times 4 is 12i. 3i times 5i is plus 15i squared, which we know is negative 15 now, because it's 15 times negative 1. So 8 minus 15 is negative 7. 10i plus 12i is 22i. So this ends up negative 7 plus 22i over 41. That's what you get when you divide those. This can be written, you could separate it. You could say it's negative 7 over 41, which is the real part of the answer. And then this is the imaginary part, 22i over 41. So that's a real and imaginary part of the answer. So either one of those are the same thing. And that's really what the second lesson is all about, is operations with these complex numbers. You can add them, you can subtract them, and then it gets down to where you can also multiply and divide. And it does talk a little bit about plotting, like on a graph. You have to have a special graph because you have to have a vertical axis that's an imaginary axis. It's like a three-dimensional graph. So for a complex a plus bi, you put a on the real axis and b on the imaginary axis. So we don't generally graph complex numbers because we don't use imaginary graphs that can do that. But you can look it up. You can Google in a graph of complex numbers and see those three-dimensional type graphing of those a plus bi numbers there. So. All right, like I said, that was a lot. I'm tired. We threw a lot at you this morning, but we have these two assignments. This also has just like a 5-question multiple choice assignment. So you just have 2 5-question assignments this week. They just deal with all of this division and complex numbers and synthetic division, real roots, rational numbers, all that stuff. So a lot thrown at you this week, but we're about finished up. So if you got questions, email me. We'll get together. Otherwise, you can review the video, and we will see you next time. It's a B Friday this week. So, bye-bye.